Log on, tune in, find out. Another good idea from Cambridge.
Thank you. Well, I mean, I won't be here long, but it's very nice to be here. Thank you very much for the invitation. And my first time in Cambridge. Anyway, so okay. Sorry, where's the chalks? Down here. Oh, all right. Yes. And the eraser is? Oh, here. Oh, okay. All right. There's lots of stuff there. All right. Thank you. Okay, so I'm going to talk a little bit about the classic Torelli problem. So the classical Torelli, it's for curves in their Jacobians. So if you are given a curve, I mean smooth projective over C, then you can define its Jacobian, which by definition I will take to be H0 of C of C dual modulo H lower 1 of CZ. And if the genus of C is G, then this is a complex torus of dimension G, and it is well known that it's actually an abelian variety, meaning it has a polarization. So this is isomorphic to C to the G modulo lattice. Okay. And the classical Torelli theorem tells you the following. And actually, it also comes with a polarization, right? This is a principally polarized abelian variety. Okay. And so what does the Torelli theorem tell you? It tells you that given two curves, two such curves, C and C prime, such that their Jacobians are isomorphic as principally polarized abelian varieties, then the curves themselves are actually isomorphic. Okay, and there are it's a very nice theorem. Torelli theorems are rarely true in this kind of their generality. So this is one of the nicest cases of the Torelli theorem. The other nice case being K3 surfaces. But most of the time it doesn't work that way. So what I mean, there are many generalizations of this. You can start with any variety, take its cohomology, and then ask whether the cohomology determines the variety. So if you have two varieties such that their polarized cohomologies are isomorphic, you can ask whether the varieties themselves are isomorphic. And then the case that I want to concentrate on today is Torelli theorem for prim varieties. So is it true? So first of all, let me tell you what's a prim variety. If I take a curve, again, C curve of genus G, then I give myself an étale double cover of this curve. And then I have a norm map. The way that the norm map is defined is by you can look at the points here, you can look at them as isomorphism classes of invertible sheaves or line bundles, right? And to those are associated divisors. So if I take something on C tilde, which is associated to a divisor, then I'm going to send it to OC. If I call my cover here, if I call it kappa, then I will associate to that OC of kappa lower star of the divisor. So that is how the norm map is defined. And it's well known that the kernel, this is a homomorphism of abelian varieties. And the kernel has got two connected components. Which I will write like this. P prime is a translate of P, and P is an abelian subvariety of JC tilde. And by definition, we call this P the Prym variety of the double cover. And I will also denote it like that. Okay, so so then you can ask the similar question that you can ask to the Torelli problem is, does the Prym variety determine the double cover? Now, if you start thinking about this a little bit, you can first start thinking about it in terms of moduli. So here, whoops, in the case of curves, the number of moduli for the curve, let me assume that the genus of C is at least 2. Then the number of moduli for the curve is 3G minus 3. The number of moduli for principally polarized abelian varieties of dimension G is G times G plus 1 over 2. So for G at least 2, this is always less than or equal to that. So there's no a priori, just dimension count, which would make Torelli impossible. But here there is actually. Here again, the number of moduli for the double covers is again 3G minus 3. It's the same as the number of moduli for the bottom curve, right? And then the number of this Prym variety here is an abelian variety of dimension G minus 1. So the number of moduli for the prim is not g times g plus 1 over 2, it's g times g minus 1 over 2. So if you compute a little bit, you'll see that if g is, well, let's see, if g is 2, for instance, what do you get here? You get 3 here, and you get 1 here. So Torelli is not possible just for dimension reasons. So you get a, you have a Torelli map. If I call Mg the moduli space of curves of genus G, and if I call Ag the moduli space of abelian varieties, principally polarized abelian varieties of dimension G, then the prim map will give me a morphism from Mg to Ag minus 1 called, I guess it's the prim map. Oh, sorry. Whoops. No. Sorry about that. This is moduli space of, okay. Rg is the moduli space of étale double covers of curves of genus G, and here I'm going, from Rg to Ag minus 1. Okay, so this is the prim map. It takes a double cover here, and it sends it to its prim variety. Right? And okay, so now if you look at the dimension count, here you have dimension 3G minus 3. Here you have dimension G times G minus 1 over 2. And the Torelli problem, the Torelli question asks whether the prim map is injective or not. To ask whether, if you're asking, if you know the prim variety, do you know the double cover? That means, is this map injective? So the injectivity isn't possible just by dimension count if G is 2, for instance. So let me write them here. G equals 2, you get 3 here, 1 here. G equals 3, what do you get? You get 6 here, and then 3, 2, you get 3 here. It's again not possible. And G equals 4, you get 4, you get 9 here. 4 times 3, you get 6 here. It's again not possible. Doesn't look very good, does it? So G equals 5, I get 12. And here I would get 5 times 2, I get 10. Looks a little bit better. You get G equals 6. Then what do we have here? We've got 15. And here we also have got 15. So the first case where it's actually possible that you could have a Torelli theorem for prim varieties is this one, right? And it's known in that case that the prim map is not injective. So that's due to Donaghy and Smith. The prim map is generically finite in this case. And the degree is 27. And you can produce some sort of bijection between the 27 points in the fiber and the 27 lines in the cubic surface. Okay. So, so it's not true in that case. Well, let's go on. What about G equals 7? Well, starting from g equals 7, the dimension on the right is going to be bigger than the dimension on the left, right? So if g is at least 7, then the dimension of AG minus 1 is strictly bigger than the dimension of RG. All right? And then in this case, we have a theorem due to many people. Debar has a proof, Welters has a proof, Friedman-Smith have a proof, and Kanev has a proof. And the theorem says that this Prym map, if G is at least 7, then P is generically injective. And this is what people refer to as generic Torelli. Okay, so generic Torelli holds. Okay, so you have a generic Torelli problem, but you can ask, well, could you possibly have the strong injectivity? Could it be injective everywhere? Well, first you're going to have to exclude hyperelliptic curves, for instance. So Mumford showed that if C is hyperelliptic, then the Prym variety of any double cover of C is either a hyperelliptic Jacobian or it's the product of such things. Or a product of hyperelliptic Jacobians. So just like here, if you just count the number of moduli for hyperelliptic Jacobians or hyperelliptic curves, then you get that by dimension count, the Prym map cannot be injective on the hyperelliptic locus. Okay? So a dimension count will give you that P is not injective on the hyperelliptic locus in any genus. Okay, well that's that. It's not going to work in general. But hyperelliptic curves are always special. Even though the Torelli theorem works in general for curves, right? Here, the Jacobian map will go from the moduli space of curves to the moduli space of abelian varieties. On the locus of hyperelliptic curves, this map is not an immersion, meaning the map on tangent spaces fails to be injective. So even that Torelli map kind of goes wrong.
You have to be careful with that statement. On the stacks, it's not.
On the stacks, yeah. Really?
About the immersion, let me repeat. On the stacks, this is not an immersion. On the course moduli space, this is an immersion. So it's kind of tricky.
So you're telling me.
If you compute the map on the tangent spaces,
Right,
you're making a computation for stacks,
Yes.
not for course moduli spaces. Of course, moduli space.
So what's the tangent space to this coarse moduli space then?
It's tricky to compute. You have to divide by the automorphism
By the
group, so you have to compute some invariance.
Well, but at the general hyperelliptic curve, the only automorphism will be the involution, right?
That's right. So you have
So-
to compute the invariance under the involution. It's
Yeah.
it's a true statement. There is a non-trivial paper proving that to number whom one of these people. On the stacks, it's
Orton Steenbrink.
yeah, exactly.
Orton Steenbrink.
Yep. Steenbrink.
I see. Okay. I will put the reference
But
here.
for stacks, in the deformation spaces, this is not an
Mhm. Okay. Very good. Another reason why stacks are better than coarse moduli spaces. So anyway, okay. So it's not injective on the hyperelliptic locus, but again, as we said, the hyperelliptic locus is often pathological. So so we're just going to exclude the hyperelliptic curves, okay? So assume from now on that C is not hyperelliptic. Okay. All right. Oops. Okay, so what happens then? There are still problems. So the first examples here were due to Bodil. He produced examples of curves of genus at most 10 of non-hyperelliptic curves. We are assuming that C is not hyperelliptic anymore. So there are double covers. There are curves, or let me say, there are double covers at which the Prym map is not injective. Okay, and what he used a very concrete construction due to Resius, the trigonal construction of Resius. To produce these examples. But the genus was up to 10, so there was still a possibility that maybe the Prym map would be injective if the genus is high enough. But then Donaghy came along, and he did what he called the tetragonal construction, which is sort of similar to the trigonal construction, but it's 1 degree higher. And here he showed that if C is tetragonal, meaning C has a degree 4 map to P1, then the Prym map, and it's under some genericity assumptions, then the Prym map is not injective at double covers of C. Okay. And here there was no restriction on the genus. This was in any genus. So then people always say yes is a very nice, very simple answer. If you ask a question and the answer is yes, you know exactly what the answer is. But if you ask a question and the answer is no, then you actually don't know what the answer is, because no can be a very complicated answer, right? So in this case, the answer to Prym-Torelli is no, but then you're going to start asking, well, what exactly is the answer? Because this thing is generically injective, where does it fail to be injective? And so Donaghy made a conjecture saying that if the Prym map fails at C tilde to C, I mean, if the Prym map is not injective at the double cover, then C is tetragonal. And he also decided. He went a little bit farther than this. He said that, well, actually, the failure of injectivity would be exactly due to the tetragonal construction. That if you have two double covers with the same Prym, then you could do a series of tetragonal constructions to go from the one to the other. Okay, and this was a little bit over-optimistic, so Vera came up with a counterexample. He constructed a plane sextic, a non-tetragonal plane sextic, where the Prym map was not injective. And the double cover, sorry, with a double cover.
Slight problem with that kind of statement. That if you say something is not injective at the point, I mean, you really need 2 points which map.
That's true.
So
it was two curves with 2 double covers.
And 2 plane sextics.
2 plane sextics, yes, that's right. So yeah, you're right. Maybe I should say it like that. So 2 plane sextics with 2 double covers. He could prove, of course, that they're not isomorphic. So these are non-isomorphic double covers. Yes, question? No?
Are the curves themselves non-isomorphic?
I think so. Yeah. This is in the final conference proceedings, I think. Yeah, and I think the curves themselves were not isomorphic. Yeah. The construction uses conic bundles over P2. So he had a threefold conic bundle, and it was a conic bundle in 2 different ways. So basically, I think it was a 2-2 divisor in P2 cross P2. So and so you have the 2 projection maps onto the 2 factors, gave him 2 conic bundles, and he could see that the discriminant curves were not isomorphic, but the Pryms were both isomorphic to the intermediate Jacobian of this threefold. So the Pryms were isomorphic, even though the discriminant curves of the conic bundles weren't. And those discriminant curves are the plane sextics that we're talking about here. Okay. All right. Okay. Now, one of the proofs of the Torelli problem for curves uses quadrics containing the canonical curve. You put the curve in its canonical space. It's cut out. I mean, if it's not trigonal and not a plane quintic, it's cut out by quadrics. And also, if you take its Jacobian, you look at the theta divisor in the Jacobian, then that theta divisor has got points of multiplicity 2. You can look at the tangent cones to the divisor at those points of multiplicity 2. They give you quadrics in the canonical space. You intersect the quadrics, you get back the canonical curve. So one of the proofs of Torelli for Jacobians uses quadrics containing the canonical curve. meaning the image of curve in the canonical linear system. So, so people ask whether you could do something similar for prims. If the genus of C is at least 7, then the theta divisor for the prim variety will also be singular. We're going to have points of 1, points of multiplicity 2. You can take the tangent cones at that divisor at those points. They will contain what we call the prim canonical curve. And you can ask whether you could maybe prove Torelli that way. So, so the prim canonical curve is the image of C in not the canonical linear system, but a different linear system. This one is isomorphic to PG minus 2, and eta is the point of order 2 on C, which gives the double cover, C tilde to C. Okay, so this is the analog of the canonical curve for the Jacobian. You have the canonical curve in here, and this is all isomorphic to PG, which can also be identified with the tangent space to the Jacobian at 0. And this one can be identified with the tangent space to the prim at 0. So there's a similar construction.
You mean PG minus 1?
This one, yes. I do. Okay. All right, so you can ask whether it's cut by quadrics. So as I said, in the case of a canonical curve, as soon as the curve is non-trigonal and not a plane quintic, then the canonical curve is cut out by quadrics, and those quadrics are generated by the tangent cones to the theta divisor at its singular points, at its points of multiplicity 2. So you could ask the same question here, and Lange and Cernesi proved that if C has Clifford index at least 3, I will explain what that is, then C is the only nonlinear component of the intersection of the quadrics containing the prim canonical curve. Okay, so now first of all, what's the Clifford index? Clifford index at least 3, that basically means that C is not a tetragonal curve and it's not a plane sextic. So it excludes exactly those things. So this here, see, this means that C is not tetragonal and not a plane sextic. Right? So then there's a natural question. Donaghy said, well, the prim map fails at tetragonal curves. Now it looks like, and then Vera said, well, it also fails at plane sextics. But what the plane sextics and the tetragonal curves have in common, they all have Clifford index. They have Clifford index at most 2. So if you exclude those, meaning Clifford index at least 3, then you get this theorem. All right. So it was a very natural question to ask: is could one just edit Donaghy's conjecture and say, well, instead of saying where is it? Oh, it's up there. Instead of saying that then C is tetragonal, can we just say C has Clifford index at most 2? think they call this modified Unagi. Then is the tetragonal, or maybe I should phrase it the way it was done in the paper, is the Clifford index of C less than or equal to 2. So that includes Vera's counterexample. It parallels the case of Jacobians, because for the case of Jacobians, you had that the curve was cut out by the quadrics if the Clifford index was at most 1. Okay, and now the theorem that I want to talk about today, which is due to myself and Lange, is that that's not the case. So for any integer n, there exists a curve C with the Clifford index of C greater than or equal to n, such that P is not injective at any double cover of C. So basically what it's telling you is that the Prym-Torelli has got nothing to do with the Clifford index. So something very subtle is going on here, because we said you see that the curve can be recovered from the quadrics containing it. So, and you know that the third divisor will give you some of the quadrics containing the curve. So what's happening here is that those quadrics that you get from the third divisor are not going to span the space of all the quadrics containing the Prym canonical curve. So that's what's going wrong here. And one of the proof of Dubar for generic Prym-Torelli actually used the quadrics. He proved that for a generic curve, then the quadrics containing the Prym canonical curve are spanned by the ones that you get from the third divisor. So at these pathological curves, that fails. They're not spanned by the quadrics containing the curve. So you've got the ones you get from the third divisor, but they don't span everything. Okay. All right, now I'll say something about the construction. How does it work? It uses what I'll call the n-gonal construction. All right. And how does that work? Well, for Riccius, you had a trigonal thing. For Donaghy, you had tetragonal. So let's do n-gonal. So what do you do? You start with a curve C, which is an n-sheeted cover of another curve Y. So this guy is just any smooth curve of genus GY. And I will call this guy rho n. And I have my double cover, whoops, sorry, that was kappa, from C tilde to C, which I called kappa. And if you have a tower of curves like this, you can construct another curve.
So rho n is degree n?
Degree n, yes. The rho n is degree n. And I will also assume that it's simply ramified. Oops. Otherwise, you would get singularities and things get complicated. So, okay. Now, how are you gonna? We're gonna construct two other double covers from this. All right. So, what do we have? We have a diagram. We can embed y inside c to the n. This is the nth symmetric power. And how does the embedding work? I can take a point little y in y, and what am I going to send it to? I'm going to send it to what I would call x1 bar plus dot 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 plus xn bar, where these are the pre-images of y inside C, where rho n inverse of y is those curves. And I will, if little y is a branch point, then one of these is repeated. Okay, I said it was simply ramified, so there can only be one point repeated here. And I'll just repeat that. So I'll get 2 times something in the divisor. Then I have the map induced by kappa to the n, from c tilde to the n to c to the n. And I'm going to make a Cartesian diagram. So I'm going to take the fiber product of these two guys over c to the n, and I will call this one x. Okay, so x is by definition the fiber product. This is a Cartesian diagram. And because rho n, we said, if you assume that rho n is simply ramified, you can actually prove that x is a smooth curve. Okay. And also, so what are the points of x? If kappa inverse of xi bar is x1 and xi and x prime I, then the element of x are of the form x1 plus xn, for instance, then I can put primes here arbitrarily. Those will also be points of x. So basically what I'm doing, I'm taking a point of y, I'm looking at its pre-image, and then I'm lifting each of those one by one to C tilde. Okay, so I take these guys. For each of them, I choose a pre-image in C tilde, and then I add those. I get a divisor on C tilde. Okay. All right, and now it can happen that x can have either 2 connected components or 1 connected component. And we're going to assume that it's got 2. So actually, maybe I should call it x tilde. Sorry, let me call this x tilde. It's a double cover. So I'm going to assume that it's got two connected components, x1 tilde and x2 tilde. You can use the Hurwitz formula, compute the genus, etc. These two guys have got the same genus. And this is a disjoint union. So all right.
So presumably you can characterize when it has one or two components.
Yes, yeah, and you can characterize it in terms of the Galois group, for instance. If the Galois group of the composite cover here factors through the Val group, then it splits up. Yeah. For P1, it's automatic. So if Y is P1, that's automatically true. Yeah. But you can construct examples where it's not true. So. Okay, so there's an involution also. I said that was a double cover. So there's an involution on x tilde. Well, what does it do if I take a point here? x1 plus, you just put primes everywhere. So z goes to z prime, which is x1 prime plus xn prime. If I had some primes somewhere, I would remove them, right? So I'm applying the involution on c tilde, and I get an involution on x tilde. And now we're going to restrict even further. If n is even, then this involution we will send x1 tilde to x1 tilde and x2 tilde to x2 tilde. So, and if n is odd, it will exchange them. So in fact, they will be isomorphic if n is odd. But if n is even, the involution leaves each of them globally invariant. So then you can quotient by it and you get new curves. So xi tilde modulo the involution, which I called prime, I guess. I will call that xi. You can compute the genus of this. And you can also prove that the involution is fixed point free if n is at least 3. So these will be étale double cover. So you get xi tilde to xi. This is an étale double cover. Okay. And the theorem that Herbert and I prove is that those étale double covers have got the same Prym variety. So and well, only in the case n equals 4. Okay. Then the Prym of c tilde to c is isomorphic to the Prym of x1 tilde to x1, which is isomorphic to the Prym of x2 tilde to x2. Now it's possible that this is still true if n is different from 4, but we haven't done it. The thing is that the proof uses the fact that each of them is isomorphic to that one. So if n is bigger than 4, then these don't have the same dimension actually. The dimension of P of C tilde to C is not equal to the dimension of P of x1 tilde to x1, but these two are equal. So as I said, our proof goes through this one. So we prove that each of these is isomorphic to that. But if n is bigger than 4, these two still have the same dimension, but we don't know whether they're actually isomorphic. It's possible that they are. But anyway. Okay, now to get counterexamples to Prym-Torelli, you still have to prove certain things. The first thing is, do they actually have high Clifford index? Because they are very special. Still, these are not generic curves. And second of all, are they actually non-isomorphic? So there are two more things you have to prove. So point one is that for generic choices, C is not isomorphic to x1. These are basically all non-isomorphic. C, x1, and x2 are non-isomorphic curves. And point two is that, so the point two is about the Clifford index. So if rho n has large ramification, remember rho n was the map from C to Y, the map that we started with. If it has large ramification, then the gonality, meaning the lowest degree of a map to P1, the gonality of C is equal to n times the gonality of Y. And second of all, the gonality is related to the Clifford index. So the gonality is always either the Clifford index plus 2 or the Clifford index plus 3. So that gives you a thing on the Clifford index. You can take Y to be an arbitrary positive genus curve, so you can make the Clifford index of Y be very large. Then the gonality of Y will be very large, which means this gonality will be large, and then this Clifford index will be large. So we'll give you Y, we'll give you C of large gonality, and that will give you C with large Clifford index. Okay, I have 5 minutes. I have 5 minutes, so maybe I'll let the audience choose what they want to hear, if they want to hear anything else. I could talk about the proofs of either of those steps, or I could answer some questions, or.
So what does large ramification mean? You assume simply ramified.
Yes, I mean a very big branch divisor.
Oh.
In terms of degree, yeah. Yeah, sorry, yeah. High degree branch divisor. Or ramification divisor.
Are there any estimates on the number of points in the fiber of a given point? I mean, could it be arbitrarily high?
Oh, you mean for the Prym map?
Yeah. Here you see
Yeah, I think
3
so.
points in the pre-image.
Yeah, here there's 3.
Can
Yeah.
that- I mean, is there a bound to that?
Not that I know. I mean, you can repeat the process, right? I mean, you did it for this one. You could, I suppose you could. Well, no, actually, this construction is symmetric. So if I repeat it with this one, the other 2 curves I will get will be those 2. So, however, if actually, yeah, I don't know. But if actually this is, if these 2 prims are isomorphic, and if you repeat the process for these, for n bigger than 4, you would actually, no, but that will give you the other dimension. No, I don't know. I don't know if a bound on the degree. Yeah. I don't think Donaghy had a conjecture on that either, yes.
But should it be finite? So where should could any of these even, could the fiber even not
Well, there are positive dimensional fibers for the
outside the hyperelliptic limits?
Yeah, on the Jacobians. Well, no, maybe not. For let me see. For trigonal curves, is it trigonal or is it tetragonal? I'm getting confused. Sorry. Right, for tetragonal curves. No, actually, for bielliptic curves, for instance, for curves that have a 1-parameter family of G14s, you can use the trigonal construction and construct 1-parameter families in the fibers of the Prim map. But those are still very special. Huh?
If the Clifford index is large enough, at least
Then
3,
I don't know.
is there a conjecture that this map is finite?
No, I don't know. I don't know of any of anyone who has proposed a bound on it either. Yeah, seems. I mean, the constructions have give you 3, but
It's safer not to make that.
that's right. It's much safer to not make a conjecture because whatever conjecture you make, it's probably wrong.
Well, I'm actually a believer in making conjectures.
You're a believer of
Yeah,
making.
I don't mind if they're wrong. It at least sort of stimulates people to try and prove them.
Or disprove
or
them.
disprove them.
Maybe it will stimulate them more to disprove them. It's much more fun to
Yes,
disprove them,
that's
right?
yes. Oh yes, yes.
Yeah. Anyway, so yeah, let's stop here. Thank you.